Imagine a liquid mixture where the molecules refuse to set still. Instead of maintaining a single structure, they rapidly snap back and forth between two distinct geometric shapes, known as conformers. Let's call them conformer A and conformer B. In this theoretical mixture, the population is heavily skewed. Conformer A makes up exactly 99% of the pool, while conformer B is a fleeting anomaly, representing just 1% of the molecules at any given microsecond. Now we subject this mixture to a chemical reaction. Conformer A is perfectly structured to create product C, and conformer B is structured to create product D. If you ask a first-year chemistry student to predict the outcome, they make a logical assumption. Because we started with an overwhelming 99% abundance of conformer A, we should naturally end up with a massive majority of product C. But physical chemistry contains a trap. Under specific kinetic conditions, that 1% minor conformer will inexplicably generate 99% of the final product, completely ignoring the starting population. Relying on ground state abundance to predict chemical yields is a dangerous thermodynamic illusion. The theoretical framework that resolves this paradox is called the Curtin-Hammett principle. However, this principle does not apply universally. It only activates under one non-negotiable kinetic boundary condition. The rate at which the two conformers flip back and forth must be vastly faster than the rate at which they actually transform into their final products. When they interconvert at this high speed, the molecules cease to act as isolated, competing factions. They function as a single, unified thermodynamic pool. Because they act as a single pool, the initial starting ratio of 99:1 becomes completely mathematically irrelevant to the final outcome. The final product ratio is dictated entirely by a different metric, the energy required to pass through the intermediate transition states. The chemical decision of which product ultimately forms does not happen in the stable starting valley. It is decided entirely at the peak of the reaction's energy barrier. This reaction coordinate diagram maps the energy barriers. The central valley shows ground states. Conformer A sits in a lower well, explaining its 99% dominance. To form product C, A climbs a steep gradient to its peak. Conformer B's upward route is much shorter. The disparity in these peak heights is the driving force of the reaction. The transition state for product C requires significantly more energy to achieve than the transition state for product D. Remember the rapid equilibrium rule. Because A and B flip so fast, any molecule of A that hits the massive energy wall for product C will simply convert back into B and attempt the easier path instead. The unified pool of molecules will relentlessly leak over the lowest available energy barrier, completely overriding the fact that 99% of the molecules started in well A. This map translates directly into the kinetic mathematics dictating the final product distribution. On the left is the output, the final concentration ratio of product D to C. The critical input variable is delta delta G double dagger, representing the exact difference in peak heights. The mathematical relationship here is not linear. The product ratio is an exponential function of that specific difference in peak heights. Because the function is exponential, even a microscopic difference in the energy required to reach the two transition states results in a massive skew in the final product ratio. Notice what is entirely missing from this equation. The starting concentrations of A and B do not appear anywhere in the math. The physical laws of kinetic control permanently sever the outcome from the starting materials. Only the peak matters. We can see this kinetic engine in action by shifting from abstract variables to a real-world physical system. This chemical equation shows a specific case study, the base-catalyzed synthesis of stilbenes from an ester precursor. To trigger an elimination reaction, we introduce a bulky base, specifically potassium terbutoxide. The empirical data from this reaction demands an explanation. It produces two products, trans-stilbene and cis-stilbene, but in a staggering 100:1 ratio. Based on the Curtin-Hammett rule, we know this 100:1 ratio cannot be explained by looking at the starting ester, which exists as a rapidly rotating mixture. If the answer lies at the transition states, what exact physical forces are pushing one peak so much higher than the other to force a 100:1 mathematical split? To solve the anomaly, we have to zoom in and analyze the precise three-dimensional geometry of the molecules at the exact microsecond of reaction. First, we examine the specific transition state pathway leading to the minority product, cis-stilbene. Look closely at the bulky functional groups involved, specifically the large space-occupying phenyl ring and the ester group. The specific geometric rotation required to form cis-stilbene forces these two massive groups into the exact same physical space. This causes severe steric hindrance, a physical repulsion between overlapping electron clouds. This physical clashing acts like a coiled spring, driving up the energy required to achieve this transition state. This is the high mountain peak. Now we pivot to the competing transition state pathway, the one leading to the major product, trans-stilbene. In this rotation, the geometry changes entirely. The massive ester group is now positioned directly across from a tiny single hydrogen atom. The result is zero steric clashing. This lack of physical resistance means a significantly lower activation energy barrier. This is the low mountain peak. Because the trans pathway has no steric clash, the unified pool of molecules simply rushes through this lower energy barrier. The purely physical reality of steric clearance dictates the transition state energies. Those specific energies plug into the kinetic exponential equation, flawlessly predicting the 100-to-1 yield and definitively proving the supremacy of Curtin-Hammett kinetics over ground state assumptions.